So in this, I will cover the following topics: brain-computer interface, human action recognition, sign language recognition, and also the applications of the same problems in deep learning. And finally, I end up my talk with talking about cloud computing with deep convolutional neural network. So my first part of my talk is the brain-computer interface. See, nowadays, when you are in a room, okay, so you can control the AC or TV or lights with the help of the remote. Correct. So now, when you're coming from outside and the temperature in the AC is, let us say, 30 degree, right? So you want to switch over to 16 degree or 18 degree, something like that, right? You are thinking. So when you are thinking, the waves will be generated from the brain, right? The signal will be generated from the brain. Similarly, when you want to switch the remote, right? I'm sorry, switch the channels in the TV, right? So you use remote, right? Similarly, you want to switch off the light. So now imagine when you are thinking, right? You want to switch on 2 lights, or let us say 3 lights. So can it automatically be done? Because the signal has been generated from your brain, right? So we have to capture those signal in a device, right? Which will be obviously analog, right? Let us assume that we are converting that into digital. So can all these things happen, right? So yes, it may happen in the future. In another 5 to 10 years down the lane, it will happen. So how this can happen, right? So for example, we have a device called electroencephalogram, right? You might have heard ECG, right? Electrocardiograph, which is for heart. And to get the signal from the brain, so we have the device called EEG, electroencephalogram. All right. So our brain is divided into 4 parts like this. You're seeing the right-hand side image, right? And here in the encephalogram device, you have the circular portion, which we call it as electrodes, right? So they are all called electrodes. So these electrodes, when you keep this in a skull, right, the head, right, these electrodes acquire the signal, right, from the user. So they will be placed like this in the brain, right? So in the skull, and from the brain, these 14 channels will occur, right? This is a simple 14-channel electroencephalogram device. So these are all some of the examples of electroencephalogram device. So here you can see, right? So these are the devices on which we have the electrodes. All right. So these are the electrodes. All right. So yes, in fact, in our lab, I'm not sure whether Partha might have covered this. Partha Pratim Roy's lecture you might have attended. Right. So we have in our lab, we have this device. So we can put the device in the head like this, and then we can get the signal, analog signal from the device. All right. And then this will be converted into the digital using the software. So in the first slide, I introduced 14 channels, EEG, right? So here you can see we have 32 channels up to 160 channels, right? So that means up to 160 electrodes. So this means when you have more number of electrodes, you can acquire very good, right, signal. That is what the idea. The signal will be very good, right? So imagine, so 14 channels I talked about. So 160 channels you will get. You get very good signal, and so from there, I mean, you can solve several problems, right? So 2 problems I'll explain. So from here you can, right, those who are interested or those who are working in brain-computer interface, you can have several problems. So for example, with my colleague Partha Pratim Roy, we have done this work called prediction of advertisement preference. All right. So suppose there are 20 songs, 20 YouTube songs are there. right? In the YouTube, you have 20 songs. I'm asking you to rank them. So what you will do, so when you will have set of participants. Yeah, you will have set of participants, and then you take the feedback from them, right? And then you will have some statistical or machine learning approach to come up with that. That is called sentiment analysis, right? Usually the data mining researchers, they do this, and you might have come across. So that's a simple thing that is going on for several years. So now the idea is, so can we the same participants, can we put the EEG, right? When they are listening the song, we put the EEG device on the scalp, and we are acquiring the data. And the same participants have to give the data also, right? Give the feedback also about the song. So you call this as a multimodal. That means we are taking a data from electroencephalogram EEG, and we also take individually, right? That you call it as a sentiment analysis. Individually, you're taking the feedback as well. So it is like EVM, electro voting machine. So which is giving the output, right? That is what exactly it's going on in the elections. We use EVM. Suppose you use ballot paper also together, right? That is a scenario. You use ballot paper as well. So that the idea is, it will be useful in two ways. Either you merge these two data and get the output, or one will be useful. One will act as a ground truth. For example, the ballot paper, whatever the result we are getting, so whether we are checking our EVM is perfect or not, right? So in a similar way, we are getting the EEG signal, right, from the participants, right, or from the subjects, and we also take their feedback, so which we call it as sentiment analysis. So it will be a bimodal or a multimodal problem. So when we apply machine learning, so we have two data here. One is the EEG data, and another one is your sentiment analysis data. So separately, you are doing your feature extraction and classification. All right. So here, when you have a EEG data, extract the features and also go for the classification algorithm. So you will get a score, let us say alpha. And from the sentiment analysis, you do same feature extraction and classification, you get beta. So now make it alpha W0 plus beta W1 will give you the rating, right? So whichever is the highest will be the first rank and second rank and so on, right? So this is how the multimodal problem is working. So you have two data, how you separately train them, right? How separately you can compute, right? You can compute the output. So when I talk about EEG, almost everybody might have seen how the ECG signals, right? So you'll get a one-dimensional data like this, right? Exactly, almost like this. And in the case of EEG, so here you can see, suppose you look at the fourth or fifth row, the rank is 2, right? Or rank 1 is the best, and rank 5 is the worst. So you are getting a moderate signal. So you are getting green in color, right? The second, the fourth row is indicating. You can look for this. I'll use the board. All right. So if you look at this, or even this, you are getting a moderate green signal, right? So that is why the rank is 2. So if you completely get, this is for 14 channels, right? So these data we got with the 14 channels. So now if you look, this is also moderately okay. So if you get a complete green signal, then the signal is good. For example, this is not good, completely red, right? And the rank is also 5. So this will determine based on the rank. So we can use this and this, right? Based on the rank, you are getting a signal. So this signal is enough to do further problems, right? Or further analysis. So if you are increasing the number of electrodes, so for example, this number of electrodes are only 14, So when you go up to 256, right, what we are using in our lab, right? So your signal, you almost get a green signal, almost. It's exactly like in your mobile, how you're getting a signal. If your signal is good, you can talk nicely, right? So if your signal goes like your 4th rank or 5th rank, I mean, you may not get, right? The 4th or 5th, you may not get the output properly, correct? In a similar way, so here in this case, in the EEG signal, so these are all better. So I can use for further process. So when you are increasing the number of electrodes, so signal will be really good, and right, so you can do further process. Also, yeah, you may ask the question. So what happened to the noise? So when you're getting, yes, you can remove the usual moving average filter or independent component analysis using this. So you can remove this. You can remove the noise. Okay. So with the help of EEG, right? So we can do feature extraction and classification data score. And similarly, with the help of sentiment analysis, because you have right, you have all the scores with you. The song may be excellent or very good or fair or poor. So accordingly, you can have, right, I mean, you can do feature extraction and classification based on those scores, or completely you can use the statistical parameters, right, to get the sentiment. So now you're fusing these two together. So one score you call it as alpha, another score you call it as beta, and you're multiplying with some weights, alpha into W0 plus beta into W1, you will get the output, and which will give you the ranking, right? So this is how we targeted one particular problem. And also, right, so if you look at the title of this work, don't just sign, use brain tool, right? Don't just sign, use brain tool. So here you can see this nowadays in the banking sector, you have right, when you're doing a transaction, so your transaction is measured based on the signature, right? So transaction will be done based on your signature, the account holder's signature. So they just check whether the signature is matching or not. Assume that you are withdrawing very high level right currency. Assume that, right, high level amount, I mean to say. So in that case, they measure, I mean, they see your signature, and then with the database, they match it. And if it is matching, yes, transaction will be done. So there is always a possibility that somebody may, right, put your signature, right? There is always a possibility, right? 5% possibility. I'm not saying even 20 or 30% possibility, even 10%, 5 to 10% possibility, or there are even more. All right. So in those cases, right, if this is a scenario, if somebody puts my signature and right, it will be matching, assume that, then they can withdraw the amount. So to avoid this, during the signature, let us assume that we are taking, for example, yeah, this is like this is like right, the user, whenever they are withdrawing, let us say 500 rupees or 1000 rupees, or let us say even 100,000 rupees, or right, they are buying a property, something like that. So we, during signature, assume that we are taking their EEG signal as well, right? During signature, how is their mentality, right? How is their mental status? So all these things we are measuring, and then we take the EEG signal. So now when the intruder or anybody, right, when they want to sign, so during that time, we are taking their EEG. So if it is matching, right, so then we can say that, yeah, this is he is authenticated user, and we can go about that. So otherwise, we have to decline the transaction. So that is what this paper about, this work about. Okay, so when we are getting a EEG signal, so assume that we are getting a EEG signal. So here we have to again go for the multimodal problem. Right? One signal is based on EEG and another signal is of the image. Right? So the EEG signal, for example, here you can use any feature extraction algorithm. So here it's a wavelet transformation, Debauche's 4 wavelet transformation. So given signal, find out its approximate part and detailed part. The first level will give you approximate part and detailed part. All right, so this will be your A and this will be your D. This is your approximation and this is your detail. Okay, so now this will be divided, further divided. The level 1 further it will be divided A and D. Right, so like this you are going. Only the approximate part you will always get the division. Right, so now from here I will extract the features. So these wavelet coefficients, alpha, right, beta, gamma, and delta, and theta. Right, so from this signal, so let us assume that you have length near about 140 or something. All right, for each value you have. Let us say this is a signal. So from this signal, I am extracting only the 4 parameters: alpha, beta, gamma, and theta. All right, so for a user, this will be a feature. For example, I am the user. So from my brain signal, they obtain this. So that's the feature extraction. Maybe some other user, it will be different alpha, beta, gamma, and theta. So let us assume that we have 100,000 users in a bank. So we are getting this, right, during their transaction. So you may ask the question, so it will be like a multivariate problem, like they may do the transaction for 500 rupees or 1,000 rupees or 100. Maybe every time you can take the common, with the statistical parameter, you can have a common signal, or separately also you can do that, because sometimes when you are withdrawing a very little amount, you may not feel tensed, right? Whereas when you are doing the transaction for the huge amount, so you may be tensed. So your signal may be right or even completely different. So in all the situations, we are measuring the signal, and from these signal, all right. So from these signal, we are extracting the features. So once you extract the features, correct. So this is based on the brain signal. Once you extract the features, you require the classification algorithm. So for example, here it is based on discrete wavelet transformation for feature extraction, and you do the classification. So who is that? Right, the user, whether or the customer, right? Out of that 1,000 customers, right? Whether in which one he or she belongs to. So for that, we require a classification algorithm. So here we use Hidden-Markov model. So this is a bimodal problem. So when you are applying a machine learning algorithm, let us say in the case of a signature, it's a PHOG plus Hidden-Markov model. That means pyramidal histogram of gradient, which will be useful for feature extraction, and classification is Hidden-Markov model. And similarly for the brain signal, discrete wavelet transformation, just now I said, for the feature extraction, and Hidden-Markov model for the classification. Right? So it's a multimodal or a bimodal problem. So it will be useful like this. For example, we are with the help of, let us say, signature. If it is not completely matching, it's like again EVM, right? Electro-voting machine only. So if the signature is not completely matching, fine, you don't need to go to the brain signal at all. Right? If it is not matching, yes, it's a forged one. You can easily find. So if it is matching, right, we are having one more check. So there you can use the brain signal. So for example, we have, this is simulated work only, 70 subjects we have taken, and then right, the age distribution go like this, and then we got the signature. One is the original one, another one is the forged one. Right, the first one you are seeing is the original, and the second one you are seeing the forged one. So even assume that the signature is matching, right, or 80-90% matching you can get, but the signal will be, the brain signal will be completely different. Similarly, third is the original one, and fourth is the D, is the forged one. Yeah, so when you apply the machine learning algorithm, right, so you can see, so we can we have tested with the several feature extraction and classification algorithm, and you can see at one point of time when you are doing a early fusion or late fusion with pyramid of histogram of gradient with EEG using Edenmargo model, at one point of time we reach 98.24% accuracy. All right. So now the researchers, in fact, even our students, start working on the similar kind of problems using the deep learning algorithm. The one I focus here is the classical machine learning approach, right, and the bimodal problem, and how you can, right, solve these kind of problems. So the first part is brain computer interface. If you have any questions, I'll just take. Okay.
Questions? Yeah.
There are no questions here. Yeah, if you have any questions, you can go ahead on the brain computer interface. Okay, so if there are no questions, I'll go to the next part. The next part is the human action or activity recognition. Right? So yeah, nowadays the CCTV or other footages like RGB video or depth video or infrared video, so they are all common, right? So nowadays, so you can see three different videos here. So here you have a RGB video where I request all the participants to mute the mic. Okay, thank you. So here you can see RGB video. A person is throwing a ball, and the second one, the person is hitting the ball, and the third one, collecting the ball. Right. So these are all some of the actions, some of the activity. Right. So here RGB, the persons are visible. Right. If you are looking at a very good video, the persons are visible. Whereas in the depth video, you can see that the people are doing action, but you cannot find who are they, right? The video is not, in fact, the faces are not visible, right? Such videos called a depth video. So it is being reconstructed from two or more images, and then it is showing only the depth. The third one is the infrared during night, right? If there are some actions, how your machine can recognize. See, for example, let us assume that we are making a machine learning algorithm on all these, and this will give you the class level. Right? For example, in the first one, a person is throwing the ball. Assume that you are given a CCTV footage, and you are finding out what are all the frames, right? The person is throwing the ball. For example, 24 hours video is given to you. So manually, it is almost impossible, right? It will take a lot of time. So now, so can I have an algorithm? So can I write an algorithm? And then can I find out, right, what are all the frames where the person is throwing the ball? Or in a cricket match, what are all the frames the batsman is hitting the sixes? Right, so these are all called the human action or activity recognition. Correct? And how do you categorize these? So what are all the levels of human activities? For example, here you have gestures. Right? Gestures is just like doing a thumbs up or stretching, nodding. These are all called the gestures. And actions, a person is hitting the ball or walking or waving. These are all called the actions. A single actor. And the third one is the interaction. Right? It may be a human-human interaction or human machine interaction, human object interaction. For example, shaking the hands of two persons to call interaction, or texting in a mobile you call interaction. It's a human machine interaction. And there are group activities, fighting, right? For example, in a football stadium, people are fighting here in this video, right? Or in an ATM, somebody is stealing the money, right? So these are all called group activities. So it starts from your gesture, the simple gesture, the lowest human activity, all right, or action, or interaction, or group, right? So to analyze all these kind of problems, which goes under the video analytics problem, right? So many are working on these kind of areas, the video analytics problem. So now we will take one problem. We call it as a human action recognition, right? Some of the humans, group of humans, or one or two human, or one human can do some actions. So suppose you are given 12 different camera views, right? So these are the 12 different, let us say, CCTV or PTC camera footages, all right? So from these footages, I want to focus on a common area. So 12 different cameras are surrounded. So that means let us assume that I'm focusing on the parking lot. All right. So it's like same concept. I mean, you have Google Map. Google Map is not a single image, right? So it has been stitched of multiple images, right? And then mosaic together, and then you are seeing as a single image. So in a similar way, I'm not saying exact way, similar way. So you have 12 different footages, and I'm finding the common area, right? So the common area is this parking lot. Let us assume that this is a parking lot. This is a common area, right? In the common area, assume that some of the human activities are going on. For example, here, right? So the persons are walking, right? So two persons are walking, and a person is walking with a shadow. Three people are walking. So now I have to first extract the dynamic objects out of it. So how do you do that? You have a optical flow algorithm. All right, I'm not going in the details about the optical flow, but whenever you have a video analytics problem, you have optical flow problem. So what do you mean by optical flow? Suppose, let us say in the ith frame. All right. So in the ith frame, assume that when I want to find out the dynamic object, ith frame, I am finding the gray level of this image, right? Gray level, it will give. For example, if I focus on, if I focus on this, assume that if I focus on this particular pixel, right? So it may be alpha, beta, gamma. The gray level values. The gray level values will be, it's like, let us say RGB image without loss of generality. Let us say RGB. If it is a gray level image, only one alpha is there, right? That you know that. So this is in the jth frame. All right. So what will happen in the j plus first frame? Right, in the j plus first frame. So this will be, right, in the case of a j plus first frame, you will get some other alpha dash, beta dash, gamma dash, the gray level value. So assume that because the person might have walked away, right? Or you may get the little bit difference. So when I take the consecutive frames, let us say R frames, R consecutive frames, so you will get the different gray level values. All right. So now I do simple subtraction. So you will get alpha minus alpha dash, which is a non-zero value, beta minus beta dash, which is also non-zero value, and gamma minus gamma dash. So all are non-zero values. Whereas, suppose if I consider, let us say, this pixel, all right? So that's a static object. Car is a static object here. So jth frame also I will have, let us say X, Y, Z. This is what my gray level values, right? And j plus first frame also it will be X, Y, Z. So when I subtract these two, I will get 0. So therefore, you are getting all these places, you are getting 0. So they are all nothing but the static object, right? The black pixels are nothing but the static object. Whereas here it will be non-zero. When you subtract, it will be non-zero. So it's almost like this. Your optical flow algorithm is almost like this. So in this way, I can find out the dynamic objects. So I can segment it out, the dynamic objects, right? Which we call it as region of interest, ROI. So whenever you are solving the machine learning problems of this kind, right? Your first aim is to find out the region of interest. All right. So here we are finding the binary image, which is also called silhouette. right? So finding the CIL out. That is a major problem here. How to find out the CIL out, right? How to find out the binary image out of it. All right. So with the help of optical flow algorithm, assume that we found out this. So once you find this, right? So assume that when I find the region of interest or the CIL out like this, right? So first I go for feature selection because I don't want to work all these 1,000 pixels. Let us say all the white pixels, maybe thousands in terms of thousands. Right? I am reducing this. Right? I am reducing. I'm selecting the features from here. So how do I select? I find the skeleton of this object, this image, this white image, the white pixels. So skeleton, now you will have tens of pixels. So thousands will be reduced to tens of pixels. Whereas the topology of both will be same. That is the idea. Right? Even though you have reduced or even though you are selecting only few, the topology will be preserved. That is the idea. So whatever problem that you are solving with this number of pixels, you can now solve with this. That is what the idea. So which is also called the feature selection. So now next you have to extract the features. All right. So from this skeleton, right? So assume that we are going to draw a bounding box. Yeah, that I will come to that. So from this skeleton, we are going to extract the features. For example, a person is walking, right? So from this skeleton, we are going to extract the features. So this is called the feature extraction. So you have a training and testing part, right, in machine learning. So during training, right, so you know that, I mean, walking sequence, train it, find out the feature vectors. And running sequence, find out the feature vectors. So you are training your model with the various videos. Right, and then when it comes for testing, because you have various training data, right, the various training features, and then when you're going for testing, it has to be matched. So for example, during testing, I got one feature vectors. So now I have to match with the feature vectors that which I've obtained during training. So for this, you require the classification algorithm, which is called, so let us say here SVM tree or LDA tree, right, or neural network. So here you have a classification algorithm. So from this classification algorithm, you can find out the action, right? So that will be recognizing the action. So this is called the action recognition problem. So this is the overview of the proposed approach or proposed algorithm. So now you have the 2D image, all right? So you have got the 2D image, and that means the binary image that I have shown here. So from this 2D image, I'll take your questions slightly later. Not sure. All right. So from this 2D image, you have to obtain the skeleton, right? How do you do that? That is what we are going to see. The first step we are going to see. So here we have done a work on, right, finding out the skeletons, right? Finding out the skeletons of a 3D object. All right. So our own work we have referred, and here we restrict to the 2D image. So in the case of a 2D image. So suppose this is an object, right? So the object is image. Suppose this is an image. The image is f of xy. All right, the image is f of xy. So now from this image, find out the partial differentiation, dou f by dou x, right? Find out the partial derivative, dou f by dou x, and also dou f by dou y, right? I have partially differentiated. You know, this is the image. Image is represented like this. So assume that all these things you know, and we compute the partial derivative with respect to x and partial derivative with respect to y. So now I write f vector based on this. I write f vector. F vector is I of dou f by dou x plus j of dou f by dou. So when I compute this, right, when I compute this, I will get a vector, right? So the vector space, the vector, right, the vectors, not a space. So vector space is completely a different concept. So vector, right, when I talk about the vector, so they all look like this. So for this image, when I compute this discrete, right, in a discrete, so you will get the vector like this. So here you can see the vectors from this direction and vectors from this direction will converge at some point, right? And for example, this point, there are 5 different directions: vector from this direction, vector from second direction, and this is the third, fourth, and several directions. Similarly, this point, right? They're converging, vectors are converging from several directions. Right. So we have to find these locus at least for, right? So these locus at least for the two convergence. Two vectors are converging. At least for two vectors are converging. For example, here no vectors are converging. In this point, no vectors are converging. Only one vector going in this direction. That's it. No two vectors are converging. Right? Whereas here I'm going to draw, right? So here at least two vectors are converging. Right? So here. Right? The curve that I am drawing, at least two vectors are converging. Right? Now we have to obtain this. So computationally we have to obtain this. Right? The problem is simple when you are viewing this, right? Visualization point of view, it looks simple, right? So computationally, right? So these are the vectors, right? These are the points where at least two vectors are converging. So imagine this is one object. So you will be given another image, third image, fourth image. So the idea is you have to obtain this. Now, so this will be the core skeleton. Right, this part will be your core skeleton. So I'll remove these, and these points are nothing but your core skeleton. Right, so this is your core skeleton. I'll remove this dot also. So for this image, right, this is your core skeleton. Right, so those who are working on video analytics problem, you might have seen, right? So you obtain the skeleton of a, for example, I want to find out what action is going on. You are finding out the skeleton, right? So in this approach, right, this is like a Newtonian potential, finding out the vectors. All right. So once you find out the vectors, you are getting like this, and then from here you can extract. So you can see the pattern. So once you obtain this f vector, capital F vector, you can see the pattern. So you are extracting this. So that you call it as skeleton. When you extract this you are calling it as skeleton. So the potential function that you are seeing over here, which is the Newtonian potential. All right. So fine. I'm not going in the detail, but from here we are obtaining a skeleton. Right. So you are getting like this. So from the silhouette, you are getting your skeleton like this. So now I'll be using ellipse as a bounding box. All right. So the reason I'm using ellipse as a bounding box, if suppose I'm using, let us say a square, right? If I use a square, you will have unnecessarily occupied by several number of black pixels, right? If it is a rectangle, same problem. So when you take a compact ellipse, right? So number of black pixels, right, or less compared to any other shape. So usually in the literature, the researchers, the video analytics researchers use the bounding object as bounding box as ellipse. So it has another advantage also. You can divide these ellipses into n different sectors. All right. So these are the n sectors. And suppose if I consider, let us say, second sector, assume that this is my second sector. In this second sector, I'll calculate the number of pixels. Right? What are all the number of pixels here? Similarly, what are the number of pixels in the n sector, n minus 1 sector, and so on. Right? So once I find, let us assume that I am in rth frame, frame number r, right? Frame number j, assume that I am in frame number j. Right? Assume that I am in frame number j. So here, this is a F2j stands for second sector. So in the second sector, what is the number of pixels? And the denominator is nothing but the total number of pixels in the skeleton, in the entire skeleton. So this is nothing but your future vector for the jth frame. So assume that I have r consecutive frames, right? Assume that I have r consecutive frames, and then the future vectors will be f1, f2, f3, fr for, and this is called f. So for example, I have a walking sequence. I am computing my future vectors like this. If it is a running sequence, my future vectors are like this. So like this, assume that we are calculating the features, right? We are calculating the feature vectors. Right? So when you're doing the training, assume that you have several other data set, you are training your data set, your model, and you obtain for a walking sequence, this is my feature vector. For running sequence, this is my feature vector. So like this, you go about it. Right? So once you get this, once you train your model, now you have to go for testing. So the testing also, you have to repeat the same thing, and then you obtain the feature vector. Now you are looking for this feature vector belong to which class, right? So that is what you require, the classification algorithm. Right? In the machine learning, this is the reason you require the classification algorithm. So here I introduce the classical one, the linear discriminant binary class. We consider a binary class. So the theory holds for multi-class also. Right? So we consider linear discriminant binary class problem. Right? We take LDA. Suppose there are two classes. Right? Yeah, the course is machine learning on computer vision. So you may be knowing all the basics. Let me assume if there are any questions you can ask. Right? Suppose there are two classes. One is the red class, the dotted red class. Another one is a square, right? The blue square class. So now I want to do the classification based on linear discriminant analysis. All right. So you know what is meant by binary class. For example, this is a binary class. One is a normal patient's X-ray image. Another one is affected by COVID-19. And you know, all right, the machine knows how to find out this. If you are to train with both the data, machine know how to do the classification. Right. So this, you can find the data set over here. Now we are solving similar kind of binary class problem. So from these two data, right? So the one I told, from these two data, assume that two classes, samples are given. Right? So sample for class omega 1 is capital X1, and sample for class omega 2 is capital X2. One is like a red color, and another one is a blue color. Right? Red color dots and blue color square. So now the first point, you compute the mean, right? So compute the mean, mu1 and mu2. That is simple, right? You assume that the set of points are given and you are computing mu1 and mu2. So these are mu1 and mu2. That's the first step. And the second step, finding out the covariance matrix. So we have set X, the point X, right? X vector. And we computed the mean mu1. So now x minus mu1 into x minus mu1, the whole transpose will be your, the summation will be your covariance matrix. So you have 1.42, right? Subtract with 3,3.8. That is your mean, right? So x minus mu1 into x minus mu1 transpose is nothing but square of that, those two, right? So 4 minus 3 and 2 minus 3.8, the whole square. So like this, you are computing for all the other points. So when you're computing for all the other points, you will get the covariance matrix for S1. Similarly, you are finding the covariance matrix for S2. Similar way, you have mu2, you have the x vector, find out, right? So we have computed first mu1, mu2, then the covariance matrix S1 and S2. So once you compute these two, you go for within class scatter matrix. Within class scatter matrix are nothing but the addition of the two classes, right? Addition of, yeah, two covariance matrices, S1 and S2. So you have S1 and S2, you add these two, right? So once you are adding these two, you will get SW, right? You S1, S2, you have computed in the previous steps, you are just adding. When you are adding this, both are 2 by 2 matrices. When you are adding these two, you will get SW. Okay, this is within class scatter matrix. Next, you have to compute the between class scatter matrix, that's called SB, with the help of means of both the classes, right? Mu1, mu2. You computed mu1, mu2. So find out mu1 minus mu2 into mu1 minus mu2, the transpose. Then you will get, right? You are getting at 29.16, 20.52, and so on. This you call it as SB, right? And SB is nothing but between class scatter matrix. So now we are computing the eigenvalue and eigenvectors of SW inverse and SB. I will tell you why this, you may ask the question, why SW inverse and SB? All right, I will write the Fisher's equation, and in that equation, I'll again come to the point. Right now, no need to worry about this, why I am computing the eigenvalue and eigenvectors of the matrix. All right, so given this matrix, so you are computing eigenvalue first, right? So the eigenvalues we are obtaining here, we know already, we have already computed SW, we have already computed SB, right? Fine. When you, once you know SW inverse and SB, and the eigenvalues are given as, obtained as 0 and 12.2007. Right. So you have got this. Now you find out the eigenvectors. So 12.2007 is the largest eigenvalue. So now you find out the eigenvectors. For 0 eigenvalue, right? So you are getting 0 eigenvalue. This is your 0 eigenvalue. So for 0 eigenvalue, the corresponding eigenvector is this. For largest eigenvalue 12.2007, the eigenvector is this. Right? So now you can see what are the usage of these, right? One is a smaller eigenvalue and another one is the largest eigenvalue. Right? Or for the largest eigenvalue, you directly compute the eigenvector. For largest eigenvalue, you can compute directly the eigenvectors, so which is 0.91 and 0.41, right? That is what we obtain. That is what we obtain. All right. Or directly you can obtain this W2 we obtain. So the same W2 will be obtained directly by computing SW inverse into mu1 minus mu2. Both are same, 0.9088 you are getting and 0.4173 you are getting. And here also you're getting the same, right? Either way you can do that. Fine. Why we have to do this, you can know that. All right. So here you can know that. Here you can know that. So we have these two classes. Right. So we have these two classes. Right. So now this is the eigenvector. The pink in color, the line is the eigenvector for the smallest value. Right. What is the smallest value? Lambda is 0. For this eigenvalue, this is the corresponding eigenvector, right? So now what I will do, I will rotate this to first axis. That means x-axis, right? I am rotating this pink line into the x-axis, the first axis. And then obviously the points also will be rotated, right? All will be rotated towards this x-axis. And now I am projecting this. So either I can say like this or project all this, right? Project all the points in this line and then rotate to x-axis. Both are same, right? The blue points, all you are projecting in this line and then you are rotating to x-axis. So now you can see that you have the blue points and red points, right? They are merging together. They have merged together. All right. And then you are trying to find out the Gaussian out of it. From the blue points, find out the Gaussian. And for the red points, find out the Gaussian. Right. They are not separable. All right. Or I can call this is a bad separability. This is an example of a bad separability. You cannot separate. I mean to say this eigenvector cannot separate. For the smaller eigenvalue lambda, I am getting the eigenvector. This eigenvector cannot separate two classes, right? We have another eigenvalue. Another eigenvalue is lambda is 12.2007. Another eigenvector, another eigenvalue is 12.2007. Let us see how that eigenvalue is working. Right? So let us see how that eigenvalue is working. For example, for the eigenvalue lambda is 12.2007. That is the largest eigenvalue, right? So this green in color is the corresponding eigenvector, right? This green line is the corresponding eigenvector for the largest eigenvalue, lambda 12.2007. So now you have the points. This is a data point, right? So now you project all these points, right? Project all these points in this line, right? When you're projecting all these points in this line, no problem, right? You will get no problem in the sense you will get here it is red, here it is blue, clearly separable. And if you take the Gaussian out of it, both are very well separable. So that means it may be a multi-class also, right? So the multi-class problem, you will get, let us say n by n, you will get n cross n, you will get n eigenvalues. So among these, you can find out the top eigenvalues, right? Or the top eigenvalue, one only. So you will get the separability, the good separability. Two classes are separable. So the meaning is, right? So if you have the clusters like this, when you are trying to project, right? I will go to the previous slide. When you're trying to project the eigenvector, which is corresponding to lower eigenvalues, right? The two-dimensional points are projected into this one-dimensional line, right? It is not a good separability. Whereas when the eigenvector is like this, the direction is like this, right? It is, of course, perpendicular to the pink line because two eigenvectors, they are orthonormal to each other, right? So when I'm taking a perpendicular to that pink line, which is a green line now, you can see that they are the points, the data points are having good separability. So that means the highest eigenvalue in the LDA, when you have the largest eigenvalue, correct? So the corresponding eigenvector of this largest eigenvalue will give you the good separability. So this will hold for a multi-class problem also, right? So you may have n eigenvalues, find out the largest eigenvalue and take the corresponding eigenvectors. That will solve the problem. So another idea is you are not able to solve the problem in, see, for example, you are given like this. Assume that you have thousands of classes. So since we are taking two different classes, problem looks simple. Assume that thousands of classes are there, thousands of clusters are there, right? So in that case, you cannot solve the problem in two dimensions. You are reducing the dimensionality. That means you are going for a one-dimensional line. In the one-dimensional line, you can find, right? In the one-dimensional line, you can find the separability, right? You can find the solution. That is the meaning. Okay. So that is called LDA, linear discriminant analysis. So now you are now comfortable with all the notation. So now, mathematically speaking, we are finding out the direction, right? That direction means that eigenvector. All right. So I am writing it as a optimization function, right? I'm writing whatever I talked about just now. I write it as a mathematical optimization function. So we are trying to maximize. That means you are finding out for the corresponding eigenvalue, the largest eigenvalue, you are finding out the eigenvector. So now here you are seeking the direction, right? The direction in the sense you have set of points, right? You have set of points, and then you are trying to project this in certain direction to somewhere, whether the line in this direction or in this direction. So you are trying to find out, right? So that is nothing but maximization of J psi. And then this maximization of J psi given by Fisher is called Fisher's equation in LDA. So that is psi transpose SB psi and psi transpose SW psi. Psi is the direction. And here you can see that this we have already seen. What we had seen? We had seen SW inverse into SB. In fact, you have found out the eigenvalue for this matrix. Right? And we are just going back to the problem. Right? So we found the eigenvalues of SW inverse in the SB. This is due to the Fisher's equation. Right? SW is in the denominator and SB in the numerator. So we are finding out the eigenvalues of this matrix. Also, you know how to compute SB. Also, you know how to compute SW. Those things we have done. Right? I'll share the slide and you can go through how you are computing SB and SW. Right? S is the matrix, right? S1, S2 are all the matrix that we had seen. All right. So this is called LDA. But the problem with LDA, all right? So for example, I'll go for only one iteration. For example, you have 4 classes: alpha, beta, gamma, and delta. Right? Assume that we have 4 classes. So I apply LDA. Once I apply LDA, maybe I will try to get 4 classes: alpha, beta, gamma, and delta. But problem is, you know, all the machine learning problems don't give a exact 100% result. Right? You may have some beta points, beta I points. You may have some gamma k points. You may have some delta z points. Right? So that means 95% of alpha points you may get. Right? The classification may be 95% accurate. Okay, I want to further improve my algorithm. What I will do, I'll grow a tree. For example, again, I will apply my LDA. The same, whatever I talk. Right? And keep on doing this. At one point of time, I have to end up with alpha. Maybe 95% will be improved to 98%. Maybe some beta gamma points, but my algorithm has improved from 95 to 98. Right? So, as a computer scientist, you grow a tree. So LDA algorithm, you know, plus grow a tree. So you call it as LDA tree. This is called LDA tree. So till you reach the leaf node, you continue your right LDA algorithm. That is the algorithm that I have devised here. Right. So your 95% accuracy will be now moved to 98% accuracy. Possible. Right. So when you stop your algorithm at one iteration, for example, this particular children, all right, you call this as a one shot. All right, single shot algorithm. Only one time you are executing your LDA. That's it, single shot. Whereas when you keep on growing the same approach, right, you keep on working on LDA, you call it as LDA tree. Right, you're growing a tree, and this concept is called LDA tree. So now coming back to our problem. Suppose I have 9 frames, right? Assume that I have 9 frames and 8 sectors. I divide my ellipse into 8 sectors. So totally I will have 72 attributes. So let us assume that we are going to work on virtual human action fill out dataset. VIHASI stands for Virtual Human Action Fill Out Database. Right? Fill out. So this database, so suppose a person is running, right? We compute first the fill out, that is a binary image, and then compute the skeleton, right? And then the skeleton is divided into 8 parts here. So totally 9 frames here. This is just for a, right, just for visualizing this. You may have 200 frames also, but suppose, assume that you have 9 frames and number of sectors are 8 in the ellipse. So total 9 into 8, you will have 72 attributes. So these 72 attributes I am plotting, right, by finding out, let us say we have already found F2J, something like that, right? F2J divided by sigma Fj for the second sector. So like this for each sector, right, each attributes I am finding the number of pixels and I'm normalizing between 0 and 1. My future vector for running sequence will be like this, right? You train the model. You train the model like this and you get the future vectors, extract the features like this. And then when you go for the classification during testing, right, when you're going for the classification, we are applying LDA tree and you get the accuracy, right? Now how far your algorithm is working. So this is how the video analytics machine learning problem works, right? So these are all some of the class action, right? These are all some of the actions. Virtual human action fill out database. These are all some of the actions, right? Running, walking, punching, knockout, hang on ball. So these are all some of the actions. Virtual human action fill out database actions. There are 20 actions. So you may have several, right? We have taken 20 actions. You may have several. So when I go for the testing, experimentation, so suppose these are all the actions. So you're seeing running, walking, right? Or 2-arm up, finding out the corresponding skeleton. First you find out the fill out, that means the binary image. All right, first you find out the fill out, that is binary image. So then you go for the skeleton and then you are finding out the features. Right, now you are finding out these, see these features will be there. Now you apply classification algorithm or LDA tree or SVM tree or neural network or deep learning. Right, not neural network, I mean to say neural network. Right, so you apply. And then this will give you the classification result. What is this? What is this? What is this? For example, right, we already trained our model. All right, suppose I'm looking for what is this. So I have to, right, apply my LDA classification algorithm and I have to find out what is this. So that will give you the person is running. Right, so this is how we have tested our algorithm. Right, so 6 actors have been used with the 12 different camera views, and if you stop your algorithm in a single shot, the single shot LDA will give you, right, the single shot LDA will give you many misclassifications. You can find so many misclassifications. 0 is no misclassification, whereas 1, 2, 3, 4, 5, your misclassification is more. Whereas if you use LDA tree, your misclassification has been reduced like anything, right? Only one class misclassification is more, otherwise you are getting zeros and ones. Fine. So now this is your common parking lot, right? Common area that you have got from your right, common parking lot you are getting from these 12 different views, right? Common parking lot that we are getting, and then if we go for the experimentation, for example, a person is running, walking, 2-arm up, 1-arm up, and sitting posture, so you can see that, I mean, the corresponding seal out. This is the corresponding seal out. From this seal out, you can get the skeleton. And from this skeleton, you obtain the features. So these are the features. So now I apply my LDA algorithm and find out what is the feature. For example, this feature is nothing but, right, a person is running. So my algorithm has to say, once you obtain the feature, you apply your LDA tree algorithm, find out what is the classification. Right, so these are your confusion matrices. And if you use a single shot, right, your accuracy is 95.8%. And if you are using, all right, and if you are using LDA tree, the accuracy is improving to 98.5%. Right, so this is the classical machine learning algorithm. Right, now you may ask the question, can we use deep learning? Yes, you can use, but before that, I'll see if there are any questions. Okay, I don't think. Okay, you have asked all the other questions. Okay, any questions you have before going into the deep learning part?
Sir, there is a question from Ashwin Yadav, sir.
Okay.
Sir, you can unmute yourself. Ashwin,
Yeah, please. Yeah, please. Please go ahead.
Sir, Ashwin Yadav, can I go ahead?
Yeah, please.
I wanted to ask, sir, what is the scope of application of GA to solve the optimization problem? Like, suppose we, instead of going for the elaborate process, is there a scope for application of GA to get the optimal solution? Do you see that?
GA for web optimal.
Not, yeah, for solving the optimization problem.
Yeah. So there are a lot of applications on GA. For example, in the computer vision, camera calibration problem. Right, computer vision, you might have heard. Maybe
yes,
you
sir,
might have heard some talk on camera calibration. Right.
Yes,
so fundamental matrix, solving fundamental matrix, essential matrix, all these places you need optimization problem. And in fact, if you go through my set of publications, along with my student who is also a professor in mathematics department at IIT Roorkee, we have solved.
So who is the professor, sir?
Sanjeev Kumar.
Achha, because I am at IIT Roorkee only. I am, in fact, sir, I'll meet you. I am at civil engineering department.
You are in civil engineering. Okay.
I am your Karthik's neighbor, sir, just on sideline.
Okay, fine. So yeah, we have done. Sir. Yeah, we will have a discussion. Okay. Yeah, there are several applications in camera calibration problem.
Right, sir. Right.
Also here you have in the machine learning also, wherever the optimization comes, you can use GA.
Right, sir. Because that has been a question in the mind since long time. Because right now also I'm solving training with the hyperparameters is a tedious process, sir. So look forward to meeting you, sir.
You are civil working under whom?
Sir, I am under Professor Kamal Jain. Actually, I am from Army only.
Okay. I know him very well. Yeah.
Sir. Right, sir. Thank you, sir.
Yeah. Any more questions? Other participants, there are 245 participants are here. Okay, fine. So what I will do, we'll take a little break. I'll take some water. Then
yes, sir. There is another question. Then later on.
Yeah, sure.
It is from chat box. Sir, first you can take.
Go ahead. It is in the chat
sir,
box.
The question is, yes, sir. The question is how to use optical flow for segmentation of ROI in image. How to use optical flow for segmentation of region of interest in image.
Yeah, that's what I told, right? I explained. I briefly explained because optical flow problem is like taking the two consecutive frames and then you have to solve the vector equation and all. So here I have given a brief explanation about that. Right? Here you can take the
Yes,
jth frame and the next continuous consecutive frame j plus first frame. If it is a dynamic object, right, you will get a difference, non-zero difference. If the difference is zero, it is a static object. So the idea is we are finding out the dynamic objects. So the optical flow algorithm will give you this dynamic object.
Okay, sir. Thank you, sir.
Okay, we will have little break. I'll take some water.
Okay, sir.
And I will continue with
Yes,
the
please. Yeah. We
deep
can
learning
have a small break of 5 minutes, Professor Bala.
2-3
and then
minutes.
we can.
No, madam,
Yeah.
2-3 minutes are enough. 2-3 minutes.
Sure,
I want to
sure.
take water. That's
Okay, as you like.
okay. Thank you all. So I have talked about the classical machine learning problem, but you may ask the same question. You can ask the question saying that can we solve all these problems with the help of deep learning? Yes, you can do that. For example, I talked about the action recognition, right? Human action recognition. So here we have some University of Texas data set, the human action data set, multimodal human action data set. Multimodal in the sense a person may be using some extra device in the hand or somewhere, right? So that will also generate a signal. So for example, here you're seeing, right, throw, push, bowling, walk, basketball, shoot, etc. These are all some of the actions. So now assume that you have RGB video, that is the input. Also the sensor data. Assume that the person is wearing something, that is what I said. That will also generate the data. And we are computing the skeleton. Now you are familiar with the skeleton because I talked about the skeleton in the classical machine learning itself. So now from this RGB video, assume that we are finding out the stacked dense flow difference image. You call it as SDFDI, stacked dense flow difference image. All right, from the video, RGB video, assume that you compute SDFDA. So 3D will become 2D, right? So 3D in the sense video, I'm considering a 3D data, right? Because every time t is equal to some seconds, you will get number of frames or more, right? So it will be converted into stacked dense flow difference image. So now I train this SDFDI using two-dimensional convolutional neural network. And you have sensor data, gyroscopic sensor data. I train this using one-dimensional convolutional neural network. And your skeleton data, we use recurrent neural network. So the combination of convolutional neural network and recurrent neural network. So this is your input layer, right? Assume that this is your input layer. So in the input layer, you have one-dimensional data, right, which your device will be generating. and RGB video is converted into SDFDI image, 2D data, and you have a skeleton, 3D data. So this is in your input layer, right? This is your input layer, right? And in the hidden layer, so this is the one-dimensional data. We are using one-dimensional convolution neural network to train this data, right? We use one-dimensional convolution neural network to train this one-dimensional data. And similarly, this two-dimensional data will be trained by two-dimensional convolution neural network. And 3D skeleton data will be trained by recurrent neural network. So now all the dimensions are different, 1D, 2D, and 3D. So to make it common, we fuse these data together, right, for the common dimension, right? And then output layer, right? This is output layer, and this is a hidden layer, right? This complete scenario is a hidden layer. The complete scenario, we call it as a hidden layer. And this is the output layer. So output layer will give you the different classes, right? The class labels. We will get the class labels. Right? Waving, clapping, squatting, all these are all the classes. And you can see at one point of time, we are getting the accuracy 97.91. All right. So I talked about classical machine learning, and here with the help of deep learning. So it's depending on the problem, right? Maybe when you use a classical machine learning, you may get 70 or 80% accuracy. All right. So because here we are using so many input layers, so many input. And similarly, you have applications on multimodal egocentric activity. So in the case of multimodal egocentric activity, for example, assume that a person is not able to see the world. All right, assume that the person is not able to see the world. And we are keeping a head-mounted camera on him or her. All right, suppose he or she is walking, right? Let us say that's called ambulation. Either walking or walking upstairs or walking downstairs in the elevator, right? You call this as an ambulation. Correct? And this is a daily activity, for example, eating, drinking, texting, and then office work like reading, writing, organizing a file, and exercise, right? Along with a head-mounted camera, assume that a person is wearing some wearable devices like a smartwatch. And then all these devices, including the camera, are connected with this device, mobile device. So now it's like a problem like a vision and language. When you are moving on a road, that zebra cross is coming, or the lights are coming, right? The signals are coming. Or when you are walking on the road, you may get the images like dosa, vada, something like this. So that is indicating that he is near restaurant. So now, based on these images, right, based on these vision, since it is connected to your mobile device, so it will be converted into text or speech. Okay, you are near restaurant. You are near, based on the metro symbol, right? Metro sign. I mean, it is giving the indication that you are near metro. So all these information, as if like the regular persons, regular human, that we are able to see the world. So can these persons, those who are not able to see the world, can do that. This is what the idea. In fact, this work, we collaborated with one university in Japan, and they provided all the data set, right? So when they take the, they in fact use the real person who cannot see the world, right? And then how can you solve these kind of problems with the help of deep learning algorithms? So here, as I said, the head-mounted camera, like a Google Glass, right? You might have heard, or you have in fact used Google Glass, right? And wearable devices, right? Second input source is the wearable devices. So now from these RGB video, let us assume that we are calculating ADI. ADI is called approximate dynamic image, and also SDI, stack difference image. So these two images you are calculating from the video, right? Also, you have one-dimensional signal, right? You have one-dimensional signal. For example, from the RGB video, you are calculating both ADI and SDI, right? Both are two-dimensional image, use 2D CNN, right? Trained with the two-dimensional convolutional neural network. And wearable device will generate this one-dimensional data, right? So I will use one-dimensional convolutional neural network to train. So we are training separately both 2D and 1D because both are two different dimensions. We have to fuse them together, and output layer we are getting the action, right? So this work appeared in Indian Conference on Vision Graphics and Image Processing, ICVGIP, right? So with the help of convolutional neural network, you can find out the actions. So accuracy is 86.5%, right? The complete data provided by the university in Japan, and yeah, we got the accuracy up to 86.5%. And the third situation, right? Infrared action recognition. Suppose, yeah, some of you are from IIT Roorkee. So this we simulated in our campus, right? During night time. Some of the actions can happen. People may fight, right? People may kicking each other, hugging, right? Hopping, or carrying a gunpoint, right? Carrying a gun, right? So these are just simulated one. So no need to panic. So these are all the simulated ones. Suppose if these actions happen, right, during night. So assume that we fix the infrared camera, and then this will alarm the security person. That is what the idea of this work, right? So these are all different actions. And then can we apply deep learning algorithm? Yes, we have done. Here it is only the infrared video, right? So here you have only infrared video. So find out stack density, right? SDFDI, I talked about SDFDI, stack difference flow, stack density flow difference image for globally as well as locally, and saliency stack difference image locally as well as globally, and train your convolutional neural network separately, right? So here you have CNN for global SDFDI, and local SDFDI you have CNN, and for SSDI, right? So here still you have, okay, this part is completely SSDI, and here you have, sorry, SDFDI, here you have local SSDI. So all you are separately doing this. Since you are doing separately, you need a common one. So fusing together and then finding out the actions. So these are the human action during night time with the help of infrared camera, right? So this work appeared in Infrared Physics and Technology journal. So what is accuracy? So here during night time, the accuracy action, right? At one point of time, we are getting 75.17% accuracy. So these are all some of the applications on your action or activity recognition problem. It's a well-known, right? Many of the researchers are still doing, right, the activity because of various applications. So these are all some of the applications I told. And the third part of my talk on sign language recognition. All right, again, in IIT Roorkee, we have a school called Anushruti, where the students, right, they cannot talk or hear. So they do the action. So they want to communicate, they do action. So which we call it as sign language, right? So here you are seeing American Sign Language. So whenever you are learning some language, initially you go for alphabets, then the bag of words, right? Then you go for sentences, then paragraphs, then essay. Then together with the grammar, you are comfortable with the language. So in a similar way, can we do for sign language? So initially you have 26 actions, right? So 26 different actions. So that is representing A to Z. This is the American Sign Language. So what are all the problems you face? So suppose a person wants to communicate, right? So this will be your region of interest, right? But in this case, our face, right, our hand and the background, all are looking almost same color, right? So do the segmentation, right? So these are the challenges we can find, right? So how I'm going to segment and how I'm going to get the region of interest. So these are all the basic pre-processing problem in image processing, right? Let us assume that we have solved those basic pre-processing problem, and then we obtain, right, this region of interest, right? So when initially you are starting your problem with 26 classes, right? Because alphabets, 26 alphabets in English, right? So which one it belong? All right. So 26 classes you have to solve. You are training and testing, getting the output. So these are all the standard machine learning algorithm. So we are trying with the various feature extraction and classification algorithms. So for example, if I do the combination of surf and SVM, right, I may start with 68.83%. I have taken only A to F, right, not all the 26 for just a display purpose. So A to F here, and then you can see the accuracy. Right, you're getting only 68.8. So you're trying to improve. Use wavelet and SVM, or you're going for wavelet to LDA, wavelet and LDA, wavelet for feature extraction and LDA for classification. You are trending 100%. So that means you are learning first alphabets, right? So then you are going for the words. Then you are going for the sentences. So the main idea here is, so to these students, you are putting your mobile in front of them. They do action. Right, mobile or any device, they do action, and that will be converted into speech. Whatever action, that will be converted into speech. That means what exactly they want to communicate. And similarly, the inverse problem. You are saying something, right? You can speak and you are saying something. So that has to reach to them with the help of action, right? Whatever you are telling, it will go as action for them. So it's an inverse problem as well. So that is called the sign language recognition. So we have done, because the available data set English and also let us say German, right? So German finger spelling, right? So it goes like this. So you have to extract the region of interest, and right, so you apply some machine learning algorithms such as random forest and support vector machine, right? So these are all the data set. Right, 35 dynamic gesture. So 30 with the single letter, right? 26 plus A dot, A double dot, something like that. This is in the German. Those who know German, you know better. And the last one is, it's more than one letter, right? So totally you will have 30 plus 5 dynamic gesture, right? So apply SVM and random forest. You can see the accuracy, right? 76.4 if it is a 30 classes, and plus 5 if you take 73.5, something like that you are getting when you are using support vector machine and random forest. Again, you ask the question, can we use deep learning algorithm? Yes, for example, here the Argentinian sign language, you have a video or an image as well as the persons are wearing some gloves, right? So the wearable device. So that will also generate a signal. So based on this, so for example, from the RGB video, I can find a motion history image. You call it as MHI or dynamic image DI or RGB motion image RGB MI, or you are obtaining from RGB video, right? So here you are extracting the features based on convolutional neural network. Using convolutional neural network, you are obtaining the features. So from the features, you use machine learning algorithm, KELM, kernel-based extreme learning, right? So you are using KELM for classification. So this means this is the combination of both deep learning and machine learning. So you obtain like this. For example, a video is there, and you are finding out MHI, DI, RGB, MI. Right, so that those things I explained in the previous slide. Motion history image is called MHI, Dynamic image is called DI, and RGB motion image is RGBMI. All right. So you are finding out first MHI, DI, and RGBMI, and then apply convolutional neural network to extract the features. All right, extracting the features, use the convolutional neural network. And then once you extract the features, you apply KELM for classification. So this is the combination of both deep learning and machine learning. Right? So deep learning for extracting the features and machine learning is for classification. Right? Machine learning algorithms for classification. So then this will give you a class label. So this work appeared in the visual computer, and you can see the accuracy goes for the Argentinian sign language 97.81%. Similarly, we have this IITR sign language for thermal data set, right? During night time, suppose they want to communicate something, right? So in the night vision, can you solve the problem? Yes, you can do that. And so we have a separate data set for IITR sign language. So now in India, so there are several languages, right? People speak, and you can get the data set. Suppose the students, if they cannot talk or hear, all right, so you can in your region, for example, I speak Tamil, right? So I have to collect the data set from them, right? How they are exactly communicating, right? That data set I have to obtain. And then, so, for example, in Tamil, you have 247 basic characters. All right. So individually, at least the basic 12 into 18, right? 12 into 18 characters plus one special character we have. First, I have to train this. Then I have to go for the words. Then I have to go for the sentences, etc. Right? So one particular language I can do. So regionally, you can use these kind of problems to solve the problem, right, that the students are facing in India. So we have several languages, right? You have Punjabi, you have Hindi, you have Malayalam, you have Kannada. So many languages we have, right? So even if you take individual problem, you can produce one PhD, each language when you solve this. So apply the same machine learning algorithms and same deep learning algorithms. But the thing is, your data set is completely different. You are using your individual language data set, right? Whereas what I have shown with the available American or Germany or Argentinian sign language. So you can think of, right, the Indian scenario. And almost I'm in the last part of my talk. It's 2 more work. So here I'll just briefly explain how the deep recurrent network can be applicable. So for example, here you can see a pair is dancing, right? Suppose assume that I have 5 minutes video, right? I have 5 minutes video, right? The blue in color saying that I have up to T minutes, T seconds, right? Now my question is, suppose 5 minutes, can I generate 5 to 10 minutes, right? From this available T seconds with the help of deep recurrent network, right? That is what you are seeing. So can I generate, right? Remaining, let us say I want to generate 10 minutes, or I have half an hour video. Can I generate, right, half an hour more, right? So this application is the prediction and the generation. That is called the prediction and generation. And the task is for prediction and generation. And what are all the applications? So you can have action recognition, virtual reality. For example, if I generate these skeletons, I can able to generate the 3D, right? So which is called as a virtual reality. So this will be useful for surveillance. This will be useful for healthcare, right? So with the help of recurrent network, deep recurrent network, so is it possible to estimate? Is it possible to predict, right, what exactly is going to happen? For example, dance, right? Any classical dance, for example, Bharatanatyam, right? First 30 minutes, I have a video. I have certain information. I know the sequence, what will happen to the next 30 minutes, right? So those who know classical dance, or let us say the classical songs, you know what are the remaining. Can you generate, right? So this is what, this has got several applications. So this we have done, and this work appeared in International Conference on Image Processing, ICIP 2020, and you can see that this is a model. In fact, if you look at the paper, you can see the deep learning model over here, right? And yeah, I can quickly go through the comparison. For example, if you use AC-LSTM, right? This was done by Zhou and others. So this is given frames, right? Given time. For example, 0 to 5 minutes. So this is the skeleton. And then let us say 5 to 10 minutes, they generate the skeleton like this. And here you can see they are all the elongated, they are all having elongated line and elongated hand and legs, right? If you look at the animation, it is not so good, right? Because of, right, you concentrate here, right? Because of the elongated, right? You concentrate here because of the elongated hands and legs, the animation is not so good. All right, whatever they have generated, whatever the prediction they have made are not so good. All right. So now the same AZ-LSTM with pose embedding algorithms seem to be okay. Right? Okay. Still, we are not much satisfied. Right? If you concentrate here, right? If you look at the animation, still, oops, sorry. Yeah, coming. So here still you have the elongated legs and hands. But whereas the variational recurrent neural network that we have used, that's a proposed one, right? So it is working really well, and you can see the predicted movements, right? They are much better than in the literature. All right, this is, we have just extended with the post embedding, and results are much better. And if you look at here, right, so this is giving the better results comparing with the original one in the literature, right? So now from here you can reconstruct, right? I talked about skeleton, right? A lot of skeleton applications you have seen in today's lecture, right? Now you can generate the 3D model from this, whatever be the predicted step, so you can generate, right? So this is one of the applications. I still have some more minutes, so I'll complete with this. So now, so far I talked about human action recognition. Right now the question is, I may not like, right? Somebody is analyzing my video. Right? Suppose I am appearing in that video, I can think of my privacy. Right? So in these cases, right, how we are going to solve the human action recognition problem. So this is now the combination of privacy. That means I'm going to have the cloud with the deep convolutional neural network. So these are all some of the basics on cloud. I'm not going in detail. I'll talk about what exactly, all right, we want to focus on this kind of problems. So far you might have seen the video is like this, and then what are all the actions? It's a usual problem, right? The problem is, in fact, they made simpler, right? All machine learning and the deep learning group, they made the problem very simple. But now, suppose I am the person, right? I may not like where somebody is analyzing or doing research on my image or my video, right? So now I use the concept called image or video obfuscation, right? I'm converting like this. If you look at here, right, nobody can make out. Suppose half an hour video is going like this. So you might have seen many news channel, if they want to hide some person or if they don't want to give right, any information about the person, they do this. So technically it is called image or video obfuscation, right? Yes, I will show the spelling of obfuscation. Yeah, that is called image obfuscation. Right, so you can do this. You can have several blocks. The given image, you can have several blocks, right? And then you use some mathematical formulation on this, right? So you can go through the slide and you can make the obfuscated image like this. So now the challenge is, if suppose half an hour video or 1 hour video is going like this, right? The task is, can you predict the human action? If this is the input, this is the video, right? If the regular video is given, right, there are several blocks. For example, I have a block size 2 by 2. Still, the privacy is not preserved. 4 by 4, still some person is appearing. And when you go, let us say 16 by 16, even you are not right happy, go for 32 by 32 block. So image size will be 7 by 7 because the original image size is 224 by 224. So now, can you do the human action recognition where the input is this? The input is given like this, correct? So obfuscated video or obfuscated image, can you do the action, right? So for example, the usual case, so far we have seen, suppose the RGB or depth image is given like this. You compute the front, side, or top on the depth image or MHI, use convolutional neural network and get the label. Right, that is what we have seen. So now the task is, obfuscated video is given to you, right? So can you do the deep learning algorithm, right? Can you run your deep learning algorithm, right? So if the image is not obfuscated, suppose the video is like this, you get 89.30% accuracy, right? Or 112 by 112. So you suppose, sorry, your video is this, the second one. I'll just rub it off. Your video is like this, you get the accuracy 89.30. Suppose the video is like this, you get the accuracy 83.02. Obviously, because almost from no information, it is saying swipe left, because the action is swipe left. Somebody is doing swipe left, but the input is this. Can your machine learning algorithm or deep learning algorithm predict the accuracy? Yes, the accuracy we are getting 83.02, even if you use obfuscated image. So this work appeared in expert systems with applications, where one of my students, Amitesh, he was working in privacy preserving, and several of Javed Imran's paper, you might have seen, he worked convolutional neural network, and we combined the concept of cloud and convolutional neural network here. So I talked several applications, right? Starting from the brain-computer interface, and then you have action recognition, sign language recognition, and some of the applications, the combination of cloud and right, CNN. If you have any questions, you please, it's over to you now. You can ask the questions. Yeah, I'm not finding anything in the chat box. Okay, if you don't have any further questions. So
Sir,
this is
again, Ashwin Yadav, sir,
Yeah,
you
yeah.
want to ask the question?
Yeah, sure.
Ashwin, sir, you can unmute yourself.
Sir, just wanted to know whether scope for direct application of these customized models like RetinaNet, etc., is there in this framework. Like you have gone into quite depth in the CNN model and all, but if we try to model it as a object detection kind of a problem and directly try to use a RetinaNet or two-stage whatever model which is there. Is that
Yeah, you can do
possible?
that. You can do that. See, literature, those RetinaNet and all available. right? Literature people have done that. You can mine certain papers.
Right.
Yeah, we have in the literature.
Thank you, sir.
Sir, another question is that can you suggest any video dataset for emotion recognition?
You please, the emotion recognition, we have done some work on Canada plus CK database, CK plus database. It's called CK plus database. Cohen Canada plus database. So that is for the standard. All right, or even if you want some more, maybe Indian scenario, we can provide you. Just send an email to me or my group. You can find my group in that GitHub site. All right, you can contact Puneet or alumni like Imanshu. They have done. So Cohen Canada plus CK, we call CK plus database. CK database is there, that's old. So CK plus database is the latest one. So you use that for emotional recognition problems.
Thank you, sir. Sir, another question is that how to extract keyframes from video based on the motion. And the
Yes,
question.
Keyframes, it is depending on the problems, right? For example, we have done the problem on video skimming. All right, video skimming means suppose 3 hours movie is there, right? I want to reduce to, let us say, half an hour, but I should know the complete content. I should know the complete story, right? So in this case, you are extracting the keyframes, right? Go through some of my papers on content-based image retrieval. All right, start from content-based image retrieval, and we have done for video skimming. So you study the work on video skimming, and then we have given several algorithms on that, right? Because if I start explaining those, it will go another 2 hours, right? So those video skimming and content-based image or content-based video retrieval problems, you can see how to extract the keyframes in the image or in a video.
Thank you, sir. Participants, is there any other question?
So this is my website, and this is my email ID, and also I have projected my lab website. So I thank all the members of Machine Vision Laboratory, IIT Roorkee, and Department of CS. Somebody's talking. Okay.
I think most probably Oja ma'am is saying something.
Saying something. Yeah.
Yes.
So if you don't have any further questions, thank you all.
Thank you very much, sir. Sir, due to some network issue, Oja ma'am has been disconnected from the meeting. Maybe she will join.
Okay.
I don't.